A silent assumption sits at the center of modern science, and almost nobody questions it. The universe is infinite, endless, stretching forever in every direction. No wall, no boundary, no final edge. That idea is repeated in documentaries, textbooks, and classrooms across the world. It sounds powerful, it sounds logical, it even sounds comforting in a strange way. But here is the crack in that belief. There is no solid proof that the universe is infinite. Not one direct observation confirms it. Not one experiment has reached beyond the limits of what we can see. And the deeper physicists look into space, the more careful they become with the word infinity, because infinity may not be a discovery, it may be a shortcut, a mathematical convenience, a way to complete equations when the real answer is still missing. The truth is far more unsettling. Scientists are not 100% sure that space goes on forever. In fact, some of the most precise measurements ever made suggest the universe could be finite, vast beyond understanding, yes, but still limited, still measurable, still shaped. This changes everything, because a finite universe does not behave the same way as an infinite one. It has structure, it has geometry, it may even have a form that bends back onto itself in ways that challenge common sense. Modern cosmology is built on the foundation of the Big Bang theory. According to the Big Bang, the universe began around 13.8 billion years ago from an extremely hot and dense state. Space itself started expanding, not into empty space, but as space. That expansion continues today. Galaxies are moving away from each other. The farther they are, the faster they move. This discovery reshaped science in the 20th century. Later, the theory of cosmic inflation was introduced. It proposed that in the first tiny fraction of a second, the universe expanded faster than the speed of light. Inflation explains why the universe looks smooth and flat on large scales. And here is where the idea of infinity gains strength. A perfectly flat universe can extend forever. Flatness became almost equal to infinity in popular science discussions. But that equation is not exact. Flat does not automatically mean infinite. It only means space is not strongly curved. Even a flat universe can still be finite if its topology is complex. That word topology hides a deep mystery. Topology is the study of shape beyond simple geometry. It asks whether space could connect back to itself, whether traveling far enough in one direction could return you to your starting point without ever crossing an edge. This possibility is rarely discussed outside academic circles, yet it is mathematically consistent with everything we observe. The observable universe adds another layer to this puzzle. We can only see as far as light has had time to travel since the beginning. That distance is about 46 billion light-years in every direction due to expansion. Beyond that boundary, light has not reached us yet. So when people say the universe is infinite, they are speaking about regions we cannot see and may never see. It is an assumption based on extending current models beyond evidence. Data from the cosmic microwave background, the faint radiation left over from the early universe, provides the most detailed map of the cosmos when it was only 380,000 years old. Satellites have measured tiny temperature fluctuations across the sky with incredible precision. These fluctuations reveal information about the curvature of space. The results show that the universe is extremely close to flat, but extremely close is not identical to perfectly flat. Small uncertainties remain. Within those uncertainties, a slightly curved finite universe is still possible. Some analyses even hint at a closed geometry, though the evidence is not yet decisive. That subtle margin is enough to keep the debate alive among cosmologists. Infinity also creates deep philosophical and physical problems. An infinite universe filled with matter would contain infinite stars, infinite planets, and infinite copies of every possible arrangement of particles. That would mean infinite versions of you, infinite histories, infinite outcomes. Many physicists are uncomfortable with this implication because it moves science into territory that cannot be tested. When a theory predicts infinite duplicates beyond observation, it becomes difficult to confirm or reject. Some researchers argue that infinity in equations signals an incomplete understanding. In physics, infinities often appear when a model breaks down. They show up in calculations of black hole centers and in early attempts at quantum gravity. In many cases, when better theories were developed, those infinities disappeared. That pattern makes some scientists cautious about accepting cosmic infinity too quickly. The universe might be huge beyond comprehension, yet still finite in total size, shaped in a way that avoids endless repetition. In this video, the discussion will unfold step by step. The evidence behind the expansion of space will be examined. The role of inflation will be explained clearly and simply. The meaning of flatness will be separated from the meaning of infinity. The concept of topology will be broken down without complex math. The clues hidden inside the cosmic microwave background will be revealed. The philosophical consequences of an infinite cosmos will be explored, and the reason why some leading physicists remain uncertain about infinity will be made clear. By the end, the familiar picture of endless space will feel less certain and more mysterious. The universe may still be grand beyond measure, but it might not stretch forever. That single shift in perspective changes how existence itself is understood. It affects how rarity is defined. It affects whether duplicates of our world exist. It affects whether space eventually curves back onto itself in a grand cosmic loop. Stay with this journey until the final moment, because the conclusion is not what most people expect. The answer is not a simple yes or no. It is a doorway into one of the deepest questions in science today. The universe may not be infinite, and if that is true, then reality is even more astonishing than endless space. Welcome to our channel, where we explore the biggest mysteries of existence with clarity and depth. If you are ready to question assumptions and see the cosmos in a new way, make sure to subscribe and join us for this exploration. Across classrooms, documentaries, and science channels, one picture dominates the human mind. The universe is endless. It has no wall, no border, no final curtain where space simply stops. It stretches beyond every galaxy, beyond every star, beyond every cluster of light we can detect. It goes on forever. That belief feels natural because space looks empty and open. When we look at the night sky, we do not see a ceiling. We see depth, we see distance, and distance feels like it never runs out. The idea of infinity fits that feeling perfectly. It tells us that no matter how far we travel, there will always be more stars, more galaxies, more darkness waiting to be filled with light. This belief is not random. It grew out of modern cosmology, especially after scientists accepted the reality of the Big Bang. The Big Bang describes a universe that began in a hot, dense state and has been expanding ever since. Galaxies are moving away from each other. Space itself is stretching. When people hear that space is expanding, they often picture it expanding into something larger. But that is not correct. Space is not expanding into a bigger container. Space itself is growing, and if it is growing now, many assume it will continue growing forever. That assumption easily turns into the idea that the universe is infinite in size. The theory of cosmic inflation made this idea even stronger. Inflation suggests that in the first tiny fraction of a second after the Big Bang, the universe expanded at an unbelievable rate, faster than light, faster than anything we can easily understand. That rapid growth would have smoothed out irregularities and made the universe appear flat on large scales. Flatness is important here. In geometry, a flat surface can extend forever. A flat plane has no built-in reason to curve back or close in on itself. When measurements showed that the universe is very close to flat, many scientists and science communicators connected that flatness to infinity. The logic sounded simple. If space is flat, it can stretch forever. Therefore, it probably does. Over time, this became the common picture. Endless space, no edge, no boundary, just infinite extension in every direction. But here is the problem. We do not observe the entire universe. We observe only a portion of it. That portion has a name. It is called the observable universe. The observable universe is the region of space from which light has had enough time to reach us since the beginning of cosmic expansion. The universe is about 13.8 billion years old, yet because space has been expanding, the distance to the farthest visible objects is about 46 billion light-years in every direction. That number surprises many people. It is larger than 13.8 billion, because while light was traveling toward us, the space between us and its source kept stretching. Still, that 46 billion light-year radius is a limit. It is not the limit of existence. It is the limit of what we can see. Beyond that boundary, there may be more galaxies. There may be more clusters. There may be more of the same structure we observe nearby. But light from those regions has not reached us yet. And maybe it never will if expansion continues accelerating. This creates tension. When people say the universe is infinite, they are extending what we observe beyond the observable horizon. They assume that what lies beyond looks similar to what lies within. That assumption is reasonable. It is supported by the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. In simple words, it looks roughly the same everywhere and in every direction, but that principle is an assumption based on what we can measure locally. It is not a direct observation of regions beyond our horizon. We cannot test those distant zones. We cannot send signals there and wait for a reply. We cannot take a photograph of the entire cosmic structure. So when infinity is declared as fact, it rests on extrapolation, and extrapolation is not proof. The geometry of space deepens this uncertainty. Geometry is not only about shapes drawn on paper, it is about the structure of space itself. According to general relativity, gravity is not a force pulling objects together in the old classical sense. Gravity is the curvature of space-time, caused by mass and energy. Massive objects, like stars and galaxies, bend the fabric of space around them. This bending affects how light travels and how objects move. On small scales, this curvature is obvious near black holes or dense stars. On large scales, scientists measure the overall curvature of the universe as a whole. There are three basic possibilities. Space can be flat, space can be positively curved, or space can be negatively curved. Flat space follows the rules of Euclidean geometry. Parallel lines never meet. The angles of a triangle add up to 180 degrees. Positively curved space is like the surface of a sphere. Parallel lines eventually meet. The angles of a triangle add up to more than 180 degrees. Negatively curved space is like a saddle shape. Parallel lines spread apart. The angles of a triangle add up to less than 180 degrees. If the universe has positive curvature, it could be finite in volume. It would not have an edge like a wall. Instead, it would curve back onto itself. This idea is difficult to picture because we are used to thinking about three-dimensional objects embedded in higher dimensions. But the analogy of Earth helps. The surface of Earth is two-dimensional. If we ignore height, it has no edge. A person can walk in one direction forever and never fall off. Yet the surface area of Earth is finite. You can walk forever on Earth, but Earth is not infinite. The same logic can apply to three-dimensional space. It could be finite, yet unbounded, no wall, no border, but still limited in total volume. That possibility is consistent with general relativity. It does not violate the equations. It does not break known physics. The strongest evidence about the shape of the universe comes from the cosmic microwave background. This faint radiation fills all of space. It is the afterglow of the early universe, released when atoms first formed and light was able to travel freely. Before that moment, the universe was a hot plasma that scattered light in every direction. Once it cooled enough for electrons and protons to combine into neutral atoms, light decoupled and began traveling across space. That ancient light is still detectable today as microwave radiation. Satellites have mapped it with incredible detail. Tiny fluctuations in its temperature reveal information about density variations in the early universe. By studying the pattern of these fluctuations, scientists can measure the overall curvature of space. The data shows that the universe is extremely close to flat. The margin of error is small. For many, this confirms the infinite model. But extremely close to flat does not mean perfectly flat. Within measurement uncertainties, slight positive curvature is still possible. Slight negative curvature is also possible. The difference is subtle, yet it matters deeply. A tiny positive curvature, even if very small, would imply a finite universe. It would mean space eventually curves back on itself over a scale far larger than the observable region. We might not detect that curvature directly because our visible patch is too small compared to the total structure, but mathematically it remains a live option. The cosmic microwave background does not force infinity. It only tells us that if curvature exists, it is very small. This leads to the idea of topology. Geometry describes local curvature. Topology describes global structure. Two shapes can have the same local geometry, but different topology. A flat sheet of paper and a cylinder made by rolling that paper share the same local flatness. A tiny creature living on the cylinder might believe it lives on an infinite flat plane if it cannot travel far enough to notice the wrapping. In the same way, the universe could be locally flat, but globally closed. Space could connect back to itself in complex ways. There are mathematical models where traveling far enough in one direction brings you back to your starting point. Light could circle the universe more than once if it had enough time. In such a cosmos, distant galaxies might appear in multiple directions as duplicate images caused by light, taking different paths around the cosmic structure. This possibility creates a strange thought. You could be seeing the back of your own galaxy without knowing it. The light might have traveled around the entire universe and returned from another angle. Scientists search for patterns in the cosmic microwave background that would reveal such repetition. They look for matching circles or mirrored structures. So far, no clear evidence of this wrapping has been found. But the absence of evidence is not evidence of absence. The scale of the universe could be so large that any wrapping occurs far beyond our observable boundary. If the total size is many times larger than what we can see, detecting its topology becomes nearly impossible with current technology. Cosmic inflation complicates the picture further. Inflation predicts that the universe expanded so rapidly that any initial curvature would have been stretched close to flatness. Many inflation models naturally produce a universe that appears infinite for all practical purposes. Some versions even lead to eternal inflation, where different regions of space keep inflating at different rates, potentially creating a multiverse. In such scenarios, infinity becomes almost unavoidable, but inflation itself is not directly observed. It is inferred from how well it explains certain features of the universe, like uniform temperature and large-scale structure. There are alternative models that attempt to explain these features without requiring eternal infinite expansion. Some inflation models predict a finite but extremely large universe. The mathematics allows both outcomes depending on specific parameters. This creates a quiet tension in cosmology. The theory most often used to support infinity can also be adjusted to allow finiteness. The difference lies in details we cannot yet measure. Tiny changes in the shape of the inflationary potential field could alter the ultimate size and fate of the cosmos. Because we do not have direct access to the physics at those extreme energies, certainty remains out of reach. Inflation is powerful, but it is not a completed story carved in stone. Beyond physics, infinity brings philosophical weight. A truly infinite universe containing matter distributed in similar patterns would require infinite repetition. Every possible arrangement of particles that does not violate physical laws would occur somewhere. That means somewhere in that infinite expanse, there would be another Earth identical to ours, down to the smallest detail. Another you reading these words. Another version of history unfolding in slightly different ways. Some scientists accept this as a natural consequence of infinity. Others hesitate. It feels less like a testable prediction, and more like a mathematical extension beyond evidence. When a theory produces uncountable duplicates that can never be observed or interacted with, its scientific status becomes more abstract. In physics, infinities often signal a breakdown in understanding. When equations explode into infinite values, it usually means a deeper theory is needed. The infinities predicted by classical physics at the center of black holes motivated the search for quantum gravity. The ultraviolet catastrophe in early physics led to quantum mechanics. In each case, infinity appeared as a warning sign that the model was incomplete. That historical pattern makes some researchers cautious about accepting cosmic infinity as final truth. Perhaps infinity appears in our cosmological equations because we lack a deeper description of space-time at the largest scales. So the honest answer to the question remains open. Is the universe infinite? We do not know. The data does not prove infinity. It allows it. It also allows finiteness. Finite models can match current observations if the curvature is small enough and the topology large enough. Infinity is often mathematically simpler. It avoids dealing with boundary conditions. It removes the need to specify a global shape. But simplicity in equations does not guarantee reality. The universe might be vast, beyond imagination. It might extend far beyond anything we will ever observe. Yet vast is not the same as endless. The difference between extremely large and truly infinite is not small. It changes how existence is understood at the deepest level, and the space beyond our cosmic horizon remains silent, offering no direct confirmation of forever. A quiet shift changes everything. If the universe is finite, then reality is not an endless repetition machine. It is not a factory producing infinite copies of stars, planets, and people. It is limited, measurable, contained in a structure we are only beginning to understand. And if that is true, then everything inside it becomes rarer than we ever believed. Every galaxy becomes more special. Every planet becomes more precious. Every moment becomes less replaceable. In an infinite universe, duplicates are unavoidable. In a finite universe, uniqueness becomes powerful. The idea that space may not stretch forever transforms the meaning of existence itself. The data does not hand us a final answer. It leaves us standing at the edge of knowledge, looking into darkness that may curve back toward us in ways we cannot yet detect. If space wraps around itself, if the cosmos is shaped in a way that connects distant regions, then the sky is not just a window into distance. It may be a mirror of a much larger structure, and that leads to a deeper question. If the universe is finite and structured, if it has a global shape, then life may be far rarer than we assume. The number of possible worlds would not be endless. The chances for complex life would not repeat forever. So are we truly alone? Or are we part of a closed cosmic design where life appears only in certain rare pockets? The edge of the universe might not be an edge at all. It may not be a wall or a drop into nothingness. It could be a curve so vast that we cannot see it bending, a boundary without borders, a limit without a line. And somewhere beyond our observable horizon, the truth waits silently, hidden not because it does not exist, but because light itself has not had enough time to deliver the answer. This question is not just about distance, it is about meaning. It is about whether reality is infinite and repetitive, or finite and rare. And until we gather deeper evidence, the universe keeps its final secret. If this journey expanded your perspective, make sure to subscribe to the channel so you never miss the next exploration into the unknown. Like this video if it challenged the way you see the cosmos, and share it with someone who loves big questions about reality. The universe may or may not be infinite, but our curiosity should be.